Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for a second, you're spending 7 long, agonizing months just trapped inside a metal tube.
Yeah, flying millions of miles through this totally dark radioactive void.
Exactly. You endure the physical toll of zero gravity, the psychological strain of isolation, and then that terrifying, fiery descent through an alien atmosphere.
Which is arguably the most dangerous part of the whole trip.
Oh, without a doubt. But then you finally touch down on Mars. You step out onto the rust-colored dirt in your multi-million-dollar pressurized suit, and, you've made it.
It's a massive achievement.
Right, but there is a massive catch, because the moment you land, you realize your ticket home is buried somewhere under your boots, and if you dig in the wrong spot, it will literally evaporate into thin air before you can even capture it.
And you will be stranded forever.
It is such a terrifying scenario.
It really is, and honestly, it is the exact nightmare that keeps mission planners awake at night. I mean, their margin for error is essentially zero.
Yeah, so today we are hunting for buried treasure. Only, this treasure isn't gold, it isn't platinum, and it's not some rare alien mineral, it's just water ice.
But on Mars, that is infinitely more valuable than gold.
Exactly. And we are charting the literal blueprint for human survival on another planet. Our mission right now is to understand exactly where humans can land, how they can endure the harsh realities of the Martian environment, and, well, most importantly, how they can guarantee that round-trip ticket.
Which is incredibly complicated.
Right. So we are going to look at the razor-thin margins of Martian geography, the wild technology we're using to look underground from orbit, and the cold, hard mathematics of just keeping astronauts alive.
Because right now, planetary scientists are staring down this really massive geographic dilemma.
Okay, let's unpack this dilemma, because it's a huge problem, right?
It is arguably the most complex real estate problem in the history of human exploration.
Yeah. Because
when you look at Mars as a destination for humans, you are immediately forced to balance two completely opposing forces.
Opposing forces like what?
Well, on one side, you have human biology and the limitations of our technology. And on the other side, you have just basic planetary physics.
The planet itself is fighting us.
Exactly.
Yeah.
Now, we know, as a definitive observable fact, that Mars has these massive continent-sized reserves of water ice at its poles. We have seen the ice caps.
Right. The pictures are everywhere.
Yeah, so if you want water in sheer, unquestionable abundance, you just go to the north or south pole of Mars.
Right. But we can't go there. That's the paradox, isn't it? The places where the water is obvious, where you can literally see it sitting on the surface, those are the exact places where human biology and solar technology will immediately catastrophically fail.
Precisely. You cannot send humans or their solar-powered habitats anywhere near the Martian poles. I mean, the environment is entirely unsurvivable.
Just because of the cold.
The cold is unfathomable. During the polar winter, the temperatures drop to minus 220 degrees Fahrenheit.
Wow.
Yeah, that is so cold that the carbon dioxide in the atmosphere literally freezes and falls to the ground as dry ice snow.
That is insane. Dry ice snow falling from the sky.
It's completely alien. And at those temperatures, materials just become brittle. Lubricants freeze solid, mechanical parts snap.
And even if you could somehow, engineer a habitat to withstand that kind of soul-crushing cold, you still have the power problem, right?
The power problem is the absolute nail in the coffin for polar bases. The sunlight at the poles is either far too weak, striking the surface at this extremely shallow angle, or it is completely absent.
Because of the tilt of the planet.
Right. The polar winter plunges the region into total darkness for months at a time.
So if you're relying on solar panels to generate all that electricity needed to keep habitats warm, run life support, recycle air.
Months of darkness is just a death sentence. Now, nuclear power is an option, of course, but relying entirely on heavy, complex nuclear reactors for a first-generation base introduces immense risk and these huge mass penalties.
Yeah, no, that makes sense. Solar power is the reliable, scalable backbone of early Martian architecture.
Exactly. So, logically, mission planners have to look elsewhere. You draw a big red X over the poles.
Yeah.
And you look toward the Martian equator, the mid-latitudes.
And you get there, and suddenly the math starts to work in your favor.
It really does. The sunlight hits at a much more direct angle, and it's strong enough to power a base year-round.
And the temperatures, while still freezing by Earth standards, they are manageable, right?
More manageable. A summer day at the Martian equator can actually get up to a balmy 70 degrees Fahrenheit.
That's a nice spring day here.
Right. It is the only geographic zone where we can realistically set up a permanent or semi-permanent human presence without instantly freezing to death or losing power.
But then you run face first into the other side of this paradox.
Yeah. The other side of the paradox is that while the mid-latitudes are friendly to our technology, they are incredibly hostile to our primary resource.
The ice.
The ice. Because of the sheer physics of the Martian atmosphere, water ice simply cannot exist on the surface at the equator for any meaningful length of time.
Okay, let's really unpack the mechanics of this because I think it's counterintuitive for a lot of people. Why can't ice just sit there in the cold?
It comes down to atmospheric pressure. The atmosphere on Mars is incredibly, brutally thin. It is roughly 1% the density of Earth's atmosphere.
1%. That's basically a vacuum.
It practically is.
Yeah.
To put that in perspective, if you stood on the surface of Mars without a pressure suit, the pressure is so low that the moisture in your lungs, your eyes, and your saliva would instantly begin to boil, even at freezing temperatures.
Oh, that's horrifying.
It's called the Armstrong limit. Because the air pressure is so staggeringly low, water just does not behave the way it does here on Earth.
Right, because we are so used to the 3 distinct phases of water: solid ice, liquid water, gaseous vapor.
Exactly. On Earth, if you leave a block of ice out in the sun on a summer day, the ambient heat transfers into the ice, and the atmospheric pressure is heavy enough to hold those water molecules together as they transition.
So the ice melts into a puddle of liquid water.
Yes, and then over time, as it absorbs more heat, that liquid water eventually evaporates into vapor. But on the Martian equator, the pressure is below what physicists call the triple point of water.
The triple point.
Yeah, and at that pressure, liquid water cannot exist. It is a physical impossibility.
So what happens to the ice then if it gets warm but can't melt?
The ice skips the liquid phase entirely. It undergoes this violent physical process called sublimation.
Sublimation.
Right. The molecules of ice are literally ripped apart by the lack of surrounding pressure. They turn instantly from a solid crystal lattice straight into a gas.
So trying to keep ice on the surface of the Martian equator is basically like trying to keep a snowman alive in a vacuum chamber.
That is a phenomenal way to visualize it.
The atmosphere literally steals it away into thin air. You can't just pile up ice and use it later. The moment it is exposed to the ambient Martian environment, the lack of pressure just causes it to disintegrate into vapor.
The vacuum chamber effect is relentless, invisible, and it is absolute.
It's like this hostile alien environment is actively fighting against the accumulation of the one single resource we need most to survive.
It really is. So if surface ice vanishes into vapor at the equator, and we absolutely have to land at the equator to survive the temperatures and generate power, the only logical conclusion left to us is that we have to look underground.
We have to find ice that is buried beneath the regolith.
Exactly. And the regolith acts as a massive thermal and physical blanket.
And regolith, just for clarity, is that dusty, rocky, jagged Martian soil, right?
Correct. It shields the ice from that brutal low-pressure vacuum and blocks the direct sublimating heat of the sun. The dirt physically holds the ice in place.
But locating this buried ice is only half the battle. I feel like to really grasp the immense life-or-death gravity of this mapping project, we need to understand exactly why we are so desperate for it.
Oh, absolutely. Because this isn't just about having water to drink.
Right, or water to rehydrate some freeze-dried space food, or even water to grow plants. You can recycle drinking water. The International Space Station does it every day.
All right, they recover almost all their water.
This is about something much bigger. This is about the ticket home.
If we connect this to the bigger picture and look at the entire architecture of a crewed mission to Mars, the whole endeavor rests on a foundational engineering concept called in situ resource utilization, or ISRU.
Basically living off the land.
Precisely. In plain terms, it means you do not bring everything you need with you. You use the resources already available at your destination.
Okay, so how does that work with the ice?
When astronauts excavate this subsurface water ice, they aren't just letting it melt and putting it through a Brita filter for their canteens. They're going to pipe that water into a massive chemical processing plant.
On Mars.
On Mars. They are going to use electrolysis, running intense electrical currents generated by those solar panels through the water to physically crack the water molecules apart.
So they separate the hydrogen gas from the oxygen gas.
Yes. And then, through further chemical synthesis, they will ultimately convert those elements into propellant. Specifically, they are manufacturing hydrazine rocket fuel.
This is the part that blows my mind every time I think about it. We aren't just looking for a well. We're looking for a gas station.
We are looking for the raw materials to build a gas station on another planet.
That is just wild.
It is. And that manufactured propellant is what they will pump into the tanks of the Mars Ascent vehicle. It is the literal fire they need to launch off the surface of Mars, achieve orbit, rendezvous with their return ship, and begin the multi-month journey back to Earth.
And to really understand why ISRU isn't just a fun, nice-to-have feature, but a mandatory requirement, you have to understand the sheer, crushing logistical nightmare of space travel. It comes down to something called the tyranny of the rocket equation.
The rocket equation is the absolute bane of every aerospace engineer's existence.
Okay, let's lay it out for the listeners, because it's fascinating. If you want to launch a rocket from Earth to Mars, you need fuel, a lot of it. The vast majority of a rocket's weight sitting on the launch pad is just the fuel needed to lift the rocket itself.
Right, the payload is just a tiny fraction at the very top.
But if you also want to bring the fuel for the return trip with you from Earth, your rocket suddenly becomes exponentially heavier.
Massively heavier, because rocket fuel is a dense, heavy liquid.
Right, so you add this giant tank of return fuel to your payload. But now your rocket is heavier, which means you need even more fuel just to lift that heavy return fuel off the Earth.
The vicious cycle.
And then you need more fuel to push it through space. And I think this is the craziest part, you need a massive, wildly heavy descent stage to safely land all that heavy, volatile liquid down onto the Martian surface without it exploding.
Exactly. Every kilogram of payload you want to land on Mars requires tens, sometimes hundreds of kilograms of fuel back on Earth just to get it there.
Yeah.
The mass requirements snowball completely out of control.
It becomes financially, structurally, and physically impossible to bring a round-trip tank of gas. You would need a rocket the size of a skyscraper just to send a few people.
The math is brutal and unforgiving. The tyranny of the rocket equation dictates, with absolute authority, that you cannot bring your return fuel with you. You must manufacture it on site.
And that reality totally elevates the stakes of this underground ice mapping project, doesn't it? It goes from an interesting geological science experiment into a matter of absolute life and death.
It is the prerequisite for the mission even existing. If a crew lands on Mars and they cannot easily locate, access, and convert that Martian ice into propellant, they are stranded permanently.
Just a chilling thought.
They will become the first humans to die on another planet, not from a crash or a suit failure, but because they simply ran out of gas. The mapping of this subsurface ice is the fundamental non-negotiable prerequisite for a round-trip ticket. Without the ice, the mission is a one-way trip.
Which brings up a really intense, incredibly visceral historical memory for me, because we have actually seen this vacuum chamber sublimation happen in real time.
Oh, you mean the Phoenix lander?
Yes. Think back to the Phoenix lander. This was a robotic mission back in 2008. Phoenix landed in a high-latitude region of Mars, way up north in the polar regions where we know the ice is plentiful.
Right, vast plains of the stuff just sitting under the dust.
Right. And Phoenix was equipped with this long robotic arm that had a metal scoop on the end of it. The scientists sent the command, the arm reached out, and it dug a shallow little trench in the dirt.
Just a small scrape, really.
Yeah, we are talking just a few centimeters down, maybe a couple of inches. And sitting right there at the bottom of the trench, it uncovered these bright, brilliant white chunks of buried ice. It was this massive moment of discovery.
It was huge news at the time.
But then, because of the exact pressure physics we were just talking about, Phoenix literally used its cameras to watch its own discovery destroy itself.
Yes, over the course of just a few days.
Exactly. Over just 3 or 4 days, taking photo after photo, the team on Earth watched as those bright chunks of ice at the bottom of the trench just shrank, blurred, and vanished into the thin Martian atmosphere. They sublimated right before their eyes.
It was a profound, almost haunting visual confirmation of the sublimation physics we knew mathematically were happening. To actually see the solid ice vanish into nothingness, it really solidified how aggressive the Martian atmosphere is toward water.
It's like watching a magic trick, but it's just brutal physics.
Exactly. But here is the critical distinction we have to make. Phoenix had it relatively easy in terms of excavation.
Because it was up near the pole where it's colder?
Exactly. Because it was at a high freezing latitude, the ice was stable enough to rest mere centimeters below the surface. A simple, weak robotic scrape was enough to expose it. The regolith blanket there didn't need to be thick.
But remember the core paradox of our real estate problem: human astronauts cannot survive where Phoenix landed.
No, they have to land closer to the mid-latitudes, near the equator. And the thermodynamics of those warmer, sunnier equatorial regions dictate a harsh reality.
The ice can't survive just 2 inches down.
Not even close. At the equator, the ambient heat penetrates much deeper into the soil, which means the ice cannot survive mere centimeters down. Over millions of years, any shallow ice at the equator has already sublimated away.
So where did it go?
The ice we need has retreated much deeper underground, seeking the colder, more stable temperatures provided by a much thicker, heavier blanket of dirt. We aren't talking about scraping the surface anymore. Astronauts at the mid-latitudes are going to have to dig much, much deeper to reach the treasure.
How deep?
We were talking a meter, maybe several meters straight, down into alien rock and permafrost.
And this is where I really have to push back a little on the rosy optimism of ISRU, because it sounds so elegant on paper, right? Oh, we'll just live off the land, dig up some ice, run some electricity through it, make rocket fuel, and fly home for dinner.
It does sound simple when you gloss over the engineering.
Right. But let's ground this in physical reality. We are talking about humans having to dig a deep hole, potentially meters underground. And they aren't doing this in their jeans and a t-shirt. They are doing this while wearing massive, bulky, highly pressurized spacesuits that fight every single movement they make.
The physical exertion is immense. Just closing your hand in a pressurized glove is a workout. You're fighting the pressure of the suit just to bend your fingers.
Exactly. And on top of the physical exhaustion, they are digging in an environment where the ice actively wants to sublimate the second it hits the air. Aren't we just racing against physics here?
We absolutely are.
Think about it. Every shovelful of dirt you move, every rock you pry out of the way, you are stripping away the protective blanket. You are exposing the ice to a vacuum chamber. By the time you get the shovel down to the ice layer, isn't it just going to boil away into vapor before you can get it into the chemical processor? You're fighting the planet itself just to get a bucket of water.
You are absolutely racing against physics. And it is a race with zero margin for error. You highlight a massive engineering hurdle. The reality is, human astronauts with shovels will probably not be the ones doing the primary extraction.
Okay, that makes sense. It would be impossible.
It is too slow, too exhausting, and the sublimation losses would be disastrous. The excavation process will likely have to be heavily automated. We are talking about designing enclosed drilling rigs, massive augers that can bore down into the permafrost, capture the ice cuttings in a sealed, pressurized chamber, and extract the water without ever exposing it to the open Martian atmosphere.
Oh, I see. So the drill itself acts as the pressure vessel.
Exactly. It creates its own microenvironment. But here is the crux of the entire problem. Before you can even design that drill, before you can calculate the torque needed to cut through permafrost, before you can worry about the sublimation rate inside the auger, you have to know exactly where to put the drill in the first place.
You can't just guess.
You absolutely cannot guess. You cannot send humans on a multi-billion-dollar, decade-long mission to Mars, hand them a drill and say, try over there. It looks promising.
Right. Let's hope for the best.
Yeah. You cannot have them blindly drilling dry holes in the regolith, hoping to strike ice while their life support clocks tick down.
Yeah.
You need precise, accurate, undeniable knowledge of what is beneath their boots before they even launch from Earth.
So if we know they have to drill deep at the mid-latitudes, how on Earth, or rather, how on Mars do we know exactly where to put the drills? If the surface looks like an endless, uniform desert of red sand and rocks, we can't just look out the window. We need X-ray vision.
We do. And since we do not have literal X-ray vision, planetary scientists have had to get incredibly creative. They have to use the next best thing in the laws of physics. Thermometers. Thermometers. There's an incredible, massive effort underway right now, led by a group called the Mars Subsurface Water Ice Mapping Team.
The SWIM team.
Yes, the SWIM team, and they are coordinated by the Planetary Science Institute. Their primary goal is to locate and map water ice hidden within the first meter, roughly the first 3 feet of the Martian surface. And they're doing this entirely from orbit, floating hundreds of miles above the planet, using thermal mapping.
Okay, here's where it gets really interesting, because I want to unpack this mechanic. It sounds like magic. How do you look at the temperature of dirt from the vacuum of space through a dusty atmosphere and deduce that there is solid ice buried 3 feet underneath it?
It relies on a fundamental principle of thermodynamics called thermal inertia.
Thermal inertia. Okay, break that down for me.
Thermal inertia dictates how quickly or slowly Different materials absorb heat, and how quickly or slowly they release that heat back into the environment. To measure this on Mars, the swim team leverages data from two highly specialized, incredibly sensitive instruments currently orbiting the red planet.
So they have satellites up there doing this.
Yes. First, there is the Thermal Emission Spectrometer, or TES, which flies aboard the Mars Global Surveyor. And second, you have the Mars Climate Sounder, or MCS, which is on the Mars Reconnaissance Orbiter.
So you have these two satellites constantly doing laps around the planet.
Constantly. For years.
Yeah.
They spend years sweeping over the Martian surface, effectively mapping the exact surface temperature of the ground below them. But here's the genius of the operation. They aren't just looking for places that are absolutely hot or absolutely cold.
Because a static temperature reading doesn't tell you what's underground.
Exactly. What they are measuring is the change. They are measuring how the surface and the lower atmosphere respond to changes in sunlight. They measure the ground as the sun comes up, they measure it at high noon, they measure it as the sun sets, and they measure it in the dead of the Martian night. And they do this across the long Martian seasons from summer to winter.
Okay, think about this. Here's a perfect analogy for this, and it's something you experience all the time on Earth. Think about walking barefoot outside on a bright, sunny summer day. You step out of your house and walk onto the dark asphalt driveway. It absolutely burns your feet, right?
Right, it gets incredibly hot very quickly.
It absorbs the heat from the sun instantly. But then your feet are burning, so you step off the driveway and onto the grass. The grass is cool. Now fast forward 12 hours. It is midnight. The sun has been down for hours. The air is chilly. If you walk back outside barefoot, what happens?
The driveway is still warm.
Exactly. The asphalt driveway is still radiating warmth against your feet. It held on to that heat for hours, but the grass is freezing cold and covered in dew. Different materials hold and release heat at completely different speeds.
That is the exact mechanic we are exploiting on Mars, just scaled up to a planetary level. On Mars, you might have a vast flat plane that looks to a standard optical camera, like identical uniform dry sand, but underground, it is not identical.
So how does the thermal data reveal what's under there?
Let's say you have a patch of dry sand that sits right on top of a massive solid slab of buried ice. That patch of sand will cool down and warm up at a completely different rate than a patch of identical sand sitting 10 feet away that sits on top of dry bedrock, or a patch sitting over loose, porous dust.
Because the ice is doing what, exactly?
Ice is a massive thermal sink. It has a very high thermal inertia compared to loose dirt. During the day, it aggressively sucks up the heat penetrating down from the sun-baked surface, and during the night, it slowly releases that heat back up. It fundamentally changes the temperature profile of the ground above it. It creates a thermal wave.
It's like throwing a blanket over a rock versus throwing a blanket over a block of dry ice. If you just look at the surface of both blankets with your eyes, the fabric looks exactly the same. You can't tell what's under there.
Right. Visibly, there's no difference.
But if you take a thermal camera and measure the temperature of the fabric over the course of a day, the blanket hiding the block of ice is going to behave radically differently. It won't get as hot during the day, and it won't cool down the same way at night.
Precisely. The thermal signature bleeds through the blanket. So the TS and MCS instruments orbit Mars, taking millions of readings, and they generate these massive, staggering data sets of thermal behavior.
And then what do they do with all that data?
The swim team then takes these raw cooling and warming rates, and they run them through complex numerical computer models. These models calculate the physics of heat transfer, allowing scientists to differentiate between a thermal curve that means just sand, one that means solid rock, one that means loose dust, and the holy grail, the thermal curve that means massive deposit of water ice hiding underneath.
It is a brilliant, indirect way to map the unseen world.
It really is.
But, it sounds like a perfect, elegant system. You orbit the planet, you take the temperature of the dirt over time, you find the ice, you hand the map to the astronauts, and you launch the rocket. But reading temperatures from orbit across a planet as dynamic, chaotic, and downright dusty as Mars isn't as simple as sticking a thermometer under your tongue and reading a clear number.
No. It is incredibly fraught with complications. The theory is elegant, but the application is deeply messy. Deriving the exact depth and concentration of buried ice from orbit is a massively complex process, and it introduces scientists to what we call the mapmaker's dilemma.
The mapmaker's dilemma. Okay, tell me about that.
Well, when you are mapping Mars, you have to embrace uncertainty, because the Martian environment flat out refuses to give you a clean, unobstructed reading.
But why is it so difficult if the physics of heat transfer are universal? I mean, if thermal inertia works the same way on Mars as it does on Earth, shouldn't the map just essentially draw itself once you collect the data?
The physics are universal, but the environment is dirty. Literally. Let's look at the incredible work being done by researchers like Hannah Sizemore. She has been deeply involved in comparing the swim team's maps with other state-of-the-art maps that use entirely different processing techniques and data sets.
And what happens when you compare them?
When you look at her analysis, you see the massive friction inherent in the scientific process. The biggest culprit, the atmosphere.
Right, because Mars is famous for its dust storms.
Exactly. Mars has global dust storms that can shroud the entire planet for months. But even when there isn't a massive storm, the Martian atmosphere is perpetually choked with fine, particulate dust suspended in the air.
It's just a dusty planet.
Yes. Now think about what a satellite is doing. It is looking down from space, trying to measure the exact infrared heat signature of the ground. But to see the ground, it has to look through miles of this dusty atmosphere. And that dust absorbs sunlight, it absorbs heat from the ground, and it radiates its own heat.
Ah, I see. So when the thermometer is looking down, it's not actually seeing a clear picture of the dirt.
No. It is looking through a thick thermal haze. The dust in the atmosphere warps the reading. It obscures the clean thermal wave radiating from the buried ice. It adds noise to the signal.
The atmosphere is essentially lying to the thermometer. It's putting a warm filter over the cold ice.
That's a great way to put it. It is adding a layer of deception. But atmospheric dust is only the first problem. Then you have differences in the orbital instruments themselves. The TES instrument and the MCS instrument were built at different times by different engineering teams, with slightly different sensitivities, different resolutions, and different operational parameters.
So they don't see the exact same things in the exact same way.
Right. Okay, so you have dirty air and you have different brands of thermometers, basically. And then finally, you have the numerical models themselves. This is the biggest variable.
How so?
Well, once you download that raw, slightly noisy temperature data from the satellite, you have to run it through a computer simulation to predict what is under the ground. But how do you program that simulation? Different teams of brilliant scientists build different computer models with completely different underlying assumptions.
Assumptions about what? Like, what are they guessing?
Assumptions about how heat moves through alien dirt. One team might assume the regolith in a certain area is highly porous, like a sponge. Another team might assume the regolith in that same area is compacted and dense, like concrete.
Because we haven't been there to dig it up and check.
Exactly. One team might assume the dust layer on top is a millimeter thick. Another assumes it's a centimeter thick. These microscopic differences in assumptions drastically alter the math of heat transfer. So you feed the same raw temperature data into 3 different models, and you get 3 different maps of where the ice is.
I honestly love this because it highlights how high-level science actually works in practice. It is not just a magical machine spitting out a single, unassailable truth. It is a messy process of debate, assumption, and interpretation.
Exactly. It's a very human endeavor.
I think a great way to understand this is to compare relying on just one instrument or one single computer model to relying on that one friend we all have who is pretty sure they know a shortcut to the airport.
Oh, I know that friend.
Right. They have a theory. They have some data. Maybe they took that road once 5 years ago. But if you blindly follow them without checking anything else, you might end up stranded on a dirt road while your flight takes off.
It's a huge risk.
If mission control just uses one thermal model, they might send a multi-billion-dollar mission to dig a completely dry hole. But if we combine multiple maps created with different assumptions, different instruments, and different data processing techniques, it's like crowdsourcing traffic data on your phone.
I like that. Explain the traffic app analogy.
So when you pull up a navigation app, it's not just using one satellite. It's pulling data from thousands of other phones on the road. If one app says there's a traffic jam, it might be a glitch. But when Apple Maps, Google Maps, Waze, and the local news helicopter all simultaneously tell you there is a massive traffic jam ahead, the noise drops away.
The consensus proves the reality.
Exactly. You become incredibly certain of the reality on the ground because multiple different systems have achieved consensus.
And that concept of consensus is exactly the methodology the swim team utilizes. They recognize the mapmaker's dilemma. They know their individual models are flawed by dust and assumptions. So they aren't looking for one perfect map. They're looking for consensus among multiple imperfect maps.
Which is much more reliable.
Yes. When you take these different thermal models and overlap them like transparencies, a fascinating critical pattern emerges. In many regions on Mars, the maps show beautiful, solid agreement. Model A says there's massive ice. Model B says there's massive ice. Model C agrees.
The traffic apps all say the road is clear.
Exactly. But in other regions, the maps wildly disagree. Model A says there's a glacier. Model B says it's bone-dry bedrock. Model C says there's ice, but it's 5 meters deep.
So what do you do as a mission planner when you are holding maps that directly contradict each other? Do you just average them out and hope for the best?
No, you absolutely do not average them out. That would be a disaster. You use those disagreements as a highly strategic guide for exploration. Hannah Sizemore and her colleague Samuel Corville helped establish a fantastic, practical rule of thumb for Mars mission planning. It's known as the robot versus human rule.
The robot versus human rule. Let's explore that.
It basically dictates how we assign risk. The places on the map where the models disagree, where the data is messy, where the thermal signatures are conflicting, where the dust might be fooling the sensors. Those zones of confusion are the absolute ideal places to send robots. Because robots are designed to solve mysteries. We send a robotic rover or a stationary lander to those chaotic zones to investigate. We tell the robot to drill into the ground, to poke the dirt, to do the chemistry. We use them as ground truth to figure out why the orbital models are failing, right? Is the dust thicker than we thought? Is the rock denser? We gather that new data, feed it back to Earth, and improve the computer models. Robots are tools of discovery. They are expendable. They don't need a ticket home. They don't need oxygen. They're designed, built, and funded to explore the maybe.
They are expendable, but humans.
Humans are not expendable. Humans require it definitely. You absolutely, under no circumstances, send a human crew to a location where the maps disagree.
Because the stakes are just too high.
The stakes are astronomically high. If the astronauts land in a zone of disagreement, they set up their solar panels, they deploy their billion-dollar ISRU drill, they bore into the ground, and the ice simply isn't there because Model A was wrong and Model B was right.
They die.
They die. They cannot manufacture the hydrazine. They cannot fuel their ascent vehicle. They are permanently trapped. Therefore, human landing sites are restricted exclusively, rigorously, to the zones of highest agreement.
You want zero debate.
Zero. We only send humans to the spots where every single model, every single instrument, and every single scientist screams in unison that ice is present.
Robots can handle a maybe. Humans need a definitely. I think that framework completely changes how you look at a map of Mars. It isn't just a topological map of dirt and craters anymore. It's a map of risk, a map of survival.
Which brings us to a revolutionary shift in how the scientific community is actually looking at and communicating this data. They are moving away from just painting colors on a map, and they are moving into the realm of hard, unforgiving math.
Right. What's fascinating here is this massive difference in terminology that we're seeing now.
This is perhaps the most fascinating evolution in planetary science right now. It is the evolution of how we communicate certainty. For a long time, the maps generated by the swim team and other organizations used a system of informal ice confidence.
Ice conf.
Yes. You would look at a printed map of Mars, and a specific region would be shaded dark blue. The legend on the map would say that dark blue indicates high confidence of buried water ice. But if you are a mission planner, you have to stop and ask, what does high confidence actually mean?
Right. It's a completely qualitative statement. It's an emotion almost. It's like checking a weather app and it just says, I'm pretty sure it's going to rain today. Or a doctor looking at an x-ray and saying, I'm highly confident that's a broken bone. It feels good, but it's not precise.
Exactly. Informal confidence in these early maps basically translated to a scientist saying, well, one mapping technique found a thermal signature here that is consistent with ice, and maybe a second technique also saw something similar, so we feel good about it.
It's just too vague for space travel.
It evaluates whether the current orbital data is merely consistent with the presence of ice. But when you are building a multi-billion-dollar multinational mission architecture that hinges entirely on the absolute necessity of extracting that ice to prevent astronauts from dying, the phrase consistent with is not a strong enough guarantee.
It's too soft. Enter Samuel Corville.
Enter Samuel Corville. His recent work represents a massive, necessary paradigm shift in planetary mapping. He is leveraging advanced probability and statistics to add rigid mathematical certainty levels to these water ice maps.
So we're moving from informal ice confidence to formal probability calculation.
Yes, we are watching the field move from the informal, qualitative, squishy language of confidence to the formal, hard, quantitative language of probability.
This is a massive distinction. And for you listening right now, I want you to really think about the difference in weight between those two words, confidence versus probability.
It changes the entire conversation in the room. Instead of pointing to a blue blob on a map and telling a room full of engineers, this area has high ice confidence, Corville's statistical approach allows scientists to point to a highly specific GPS coordinate on the Martian surface and make a definitive statement.
Like what?
They can say, based on our aggregated models and atmospheric data, we have a 64% chance of finding ice if we land precisely at this location.
So what does this all mean for the people actually sitting in mission control? How does a hard percentage change the way a landing site is chosen compared to just a high confidence color on a map?
It changes everything because a hard percentage is the native baseline language of risk managers. When you are dealing with human spaceflight, you are dealing with the most risk-averse organizations on the planet.
Yeah, everything is calculated.
Every single component of a rocket, every orbital trajectory, every valve in the life support system is calculated to an exact statistical probability of failure. Mission planners do not deal in feelings. They do not deal in confidence. They deal in actuarial tables, stress limits, and failure rates.
So if you tell a flight director, we are highly confident the ice is there, they literally don't know what to do with that information.
They don't. They can't plug highly confident into their risk matrix software. It's a useless metric for engineering a survival plan. But if you tell a flight director that there is a 64% probability of finding ice at landing zone alpha, they know exactly what that means. The math is instantly clear to them.
It means there's a 36% probability that the ice is not there.
Exactly. It means there is a 36% probability of total mission failure, loss of a multi-billion-dollar asset, and the agonizing death of the crew due to lack of rocket fuel.
And a 36% chance of dead astronauts is utterly unacceptable.
Completely unequivocally unacceptable. NASA, ES, and other space agencies operate on much tighter margins. Depending on the mission parameters, they might require a 95% or a 98% or even a 99% statistical probability of ice presence before they will even consider green-lighting a coordinate as a potential landing site.
Wow, 99%.
Corville's formal quantification of probability allows the engineers, the actuaries, and the mission planners to actually do their jobs.
It gives them a threshold.
Yes, it allows them to mathematically set a threshold for human survival, say 98%, and then rigorously search the maps for the very few, very rare isolated places on Mars that actually meet that mathematical threshold.
Yeah.
You cannot gamble a multi-billion-dollar mission in human lives on a feeling about a map. You need the hard, unforgiving statistics to prove the treasure is buried exactly where you say it is before the rocket ever leaves the pad.
Okay. So let's review where we stand. We have the orbital thermometers scanning the ground for decades. We have multiple highly sophisticated computer models crowdsourcing the data to filter out the atmospheric dust and the thermal noise. And now, thanks to this paradigm shift, we have hard, rigorous statistical probability telling us exactly what the mathematical chances are of finding ice within that first meter of alien soil.
It is an incredible technological achievement.
It sounds incredibly robust. It sounds like we have it figured out,
Yeah.
but this is where the story takes a deeply frustrating, almost terrifying turn.
It does.
Because we have the statistics for that top layer, and we know we have data for the deep, deep underground. But there's a glaring, terrifying blind spot right in the exact place we might need to dig.
This brings us to a massive, critical limitation of our current technology. It is a concept that engineers and planetary scientists refer to as the missing middle.
The missing middle. It's basically an engineering gap that we currently cannot close.
Exactly. Let's look at the parameters of what we actually truly know. All of the incredible thermal data we just spent time discussing, the TES and MCS instruments, the cooling and warming rates, the crowdsourced models, the statistical probability maps, all of that brilliant cutting-edge science is entirely limited to the shallow subsurface.
How shallow?
It only probes the first 1 meter of the Martian surface that is roughly 3 feet deep.
3 feet, that's it.
Yes. The physics of thermal inertia, the way the sun's heat penetrates the ground and bounces back, simply doesn't reach deeper than that. The thermal wave dissipates. So the thermal maps tell us with incredible statistical accuracy what is happening right beneath the crust from 0 to 3 feet down.
Right. And if we want to look deeper, say 20 feet down.
If we want to look deeper, we have to abandon thermometers entirely and rely on completely different technology.
Yeah.
We use ground-penetrating radar. We currently have radar instruments orbiting Miles, like the Sherrod instrument.
And how deep does that see?
Those radars are fantastic at blasting radio waves deep into the crust and mapping vast ancient glaciers and massive deposits of ice at depths greater than 5 meters.
5 meters is about 16 feet.
Exactly. So, to summarize our vision, we have high-resolution thermal data that clearly sees the ice that is very shallow from the surface down to 1 meter. And we have powerful radar data that clearly sees the ice that is very deep from 5 meters and below.
I know exactly where you're going with this, and as someone who likes a complete picture, it is absolutely maddening.
There's a total impenetrable blind spot between 1 meter and 5 meters. Between 3 feet and 16 feet deep, we are essentially blind.
We just can't see anything in that zone.
Nothing. The thermal data from the thermometers can't penetrate that deep into the dirt, and the long radio wavelengths of the current orbital radars can't resolve anything that shallow. The radar waves just blast right through that top layer without bouncing back.
Let's really stop and agonize over this gap for a second, because the practical implications for astronauts are brutal. We established at the very beginning of this conversation that astronauts have to land at the equator to survive, and because of the warm temperatures there, the ice has to be buried deep enough to survive sublimation. While 1 meter deep might not be deep enough at the equator. The summer heat might bake that first meter and sublimate the ice away. And 5 meters deep, 16 feet, might be way too deep for an automated drill to reliably reach without breaking down, hitting bedrock, or consuming too much power.
It is a serious logistical problem.
It is entirely possible, perhaps even highly probable, that the perfect, stable, abundant ice deposits that humans so desperately need to survive are sitting right at 3 meters deep.
That is the nightmare scenario.
3 meters down, not too deep for a drill to reach, but deep enough to be perfectly protected from the heat and the vacuum.
Right.
It could be the absolute Goldilocks zone for Martian ice excavation.
Exactly. The Goldilocks zone might perfectly, cruelly align with our technological blind spot. The massive block of ice that human explorers need to survive, to manufacture their propellant, and to fuel their return rocket might be situated right at that 3-meter mark. And right now, sitting here today, we literally cannot see it.
It's just a blank space on the map.
We have beautifully detailed maps of the very surface. We have beautifully detailed maps of the deep subsurface. And we have a vast, unknown, blurry void right where the shovels and the drills need to go.
It feels incredibly vulnerable, doesn't it? We are planning the greatest leap in human history, and we have to accept that our treasure map has a massive 4-meter-thick smudge right in the middle of it.
You recognize the flaw, you acknowledge the vulnerability, and you engineer a solution. That is what aerospace engineering is. The solution to the missing middle isn't better computer models or better statistics.
So what is the solution?
The solution is the development of a completely new physical instrument. To close this critical engineering gap, the scientific community desperately needs to design, fund, and fly a high-frequency radar system.
Because high-frequency waves behave differently than the ones we're using now.
Yes, a high-frequency, short-wavelength radar would be specifically tuned to detect the density changes of ice in that exact 1 to 5 meter depth range. It would fill the gap. But building and launching a new planetary orbiter is not a fast process.
No, it takes years.
It takes years of design, billions in funding, and months of travel time. Until that new high-frequency radar is built, launched, and spends years orbiting Mars, gathering and transmitting data back to Earth, we have to accept the current reality.
And the current reality is that we are operating with incomplete data. We are planning a survival mission while partially blind.
We are. But it is deeply important to remember context here. Yes, the gap is frustrating. But until that new radar arrives, the current probability maps generated by the SWIM team, complete with all their atmospheric uncertainties, their thermal haze, and their 4-meter blind spots, are the absolute best tools humanity has ever created.
They really are.
They represent a monumental, almost unbelievable scientific achievement. We are literally wringing the hidden secrets of the deep subsurface out of the ambient temperature of alien dirt from millions of miles away.
It is a testament to human ingenuity. So let's bring this all together and look at the blueprint we've charted today. We started with a fundamental existential problem. Humans need to land near the Martian equator to keep their solar panels functioning and their habitats warm. But the water ice they absolutely require to manufacture rocket fuel cannot survive on the surface there. It violently sublimates into the thin, low-pressure air. So the ice retreats underground, safe beneath a blanket of regolith, and we have to hunt for it.
And we hunt for it by reading the temperature of the planet from space. We analyze how the Martian sand and rock absorb and release heat into the freezing night, exploiting thermal inertia to reveal the invisible thermal shadow of the ice below.
We filter out the dust and the conflicting computer models by sending expendable robots into the unknown zones, reserving the zones of total consensus exclusively for human crews.
And finally, we translate those zones of consensus into cold, hard statistics. We move past the squishy feeling of being confident, and we calculate the exact mathematical probability of finding the ice we need.
We demand a 99% guarantee of survival, even while acknowledging the terrifying, frustrating blind spot in our radar. We are building the entire architecture of human survival on a foundation of thermodynamics and probability.
Consider what this means about human exploration. For centuries, explorers sailed into the unknown relying on instinct and the stars. Now, before a single human boot touches the Martian dust, we are literally calculating the exact statistical probability of our own survival. We aren't just mapping water, we are mapping the exact boundaries of human risk. Next time you look up at the night sky, ask yourself, when we finally go, will we go because we are brave, or will we go because the math finally hit 100%?
That is an incredible thought to end on. The romance of exploration giving way to the cold, hard math of survival. We've covered a massive amount of ground today, from the vacuum chamber of the Martian equator to the thermodynamics of dirt and the agonizing reality of the missing middle. The universe is hostile, but human ingenuity is relentless. Keep looking up, keep asking questions, and never stop wondering what's hidden just beneath the surface. Stay curious.